Okay, here we go with the final question that I set. So special effects in the movie require a ball to explode in mid-air after it's been thrown. Exciting. So they got a strong spring inside it to push the two halves apart. So it splits into different masses and they travel at different velocities. And the only external force on the ball is gravity. So there are no external forces. So for question A, discuss whether momentum and or kinetic energy is conserved during the explosion. This is a bit tricky. There is an external force acting, so you could say that momentum is not conserved because there is an external force acting. But if this happens instantaneously, so these two sections are moving apart, so from not moving apart to moving apart instantaneously, which is physically impossible, then the momentum will be conserved because this is an internal force. But the whole time, weight force is acting, so you go either way with the momentum. Kinetic energy, though, is not conserved. The reason for this is that there must be some sort of energy stored up in the spring in this ball, and as soon as that energy is released, causing these balls to move apart, then kinetic energy is not conserved. You could also see that as the velocities change in this system as well. Okay, so on to B. Calculate the horizontal momentum of the system of the two pieces immediately after the explosion. Well, it says somewhere up here it happens instantaneously. Where is it? A fraction of a second after the split. So we'll just call this instantaneous, which means we can say that the total momentum of the system here is the same as the total momentum of the system here, which means I can just calculate the momentum of the system here, and that's my answer for the total momentum of the system there. So P equals mv, and just using these values here, 0.105 times 67 equals, no, go away. Great. Moving on to C. Piece A has that mass and it's travelling at 80 meters per second at that angle as shown. By drawing a vector diagram, show how you could calculate the velocity of piece B immediately after the explosion, and we don't actually need to do the calculation. Okay, so let's have a look. We've got this along here is the total, and that's equal to the previous question up there. Great, and then these other two momentums, these must add to give this momentum. So the way we do that is like this. So this is momentum A, and if we add to that momentum B, this angle in here is theta A. Great, now we don't know if this is a right angle, which is why they're not expecting us to calculate the answer. So drawing a vector diagram, show how you could calculate the velocity of piece B immediately after the explosion. Okay, so we need a bit more information on here to show how we could calculate this. So we do this. The momentum here is equal to the mass of this section times its velocity. Cool. So the next step would be to, in here, the momentum here is equal to the mass of B, which, do I have to do maths to work that out? Yes, I do. Mass of B times the velocity of B, which means B equals momentum of B divided by the total mass, 0.105, minus the mass of A, because it's B must be the difference between the two masses. Cool. So that is the answer there. Okay. So you first need to calculate PB from the vector diagram, and then you calculate the velocity of B. Okay, on to the next question. Now consider the effect of gravity as the two pieces fall to the ground. A side view of the path of pieces of piece A is shown in the diagram below. As piece A falls from P to Q, the vertical component of its momentum increases by 3.1 kg meters per second. Discuss the impulse on piece A, which is the change in momentum, as it falls from P to Q, explaining the cause of the impulse and the effect the impulse has on the momentum of A. Okay, so it's a bit of a vague question. The change in momentum, or the impulse, is 3.1 kg meters per second. Great. So the cause of this? Well, the cause of this is the weight force. We have the object A moving in projectile motion. It's the initial velocity, and it moves like so towards the ground, following projectile motion from point P down to point Q. So I guess we can think of this as the initial momentum, and down here this is the final momentum. Now the momentums are in the same direction as the velocity of the objects, because when we look at the equation for momentum, P equals mv, velocity is the only vector quantity on this side. Mass is a scalar, so the momentum vector must be in the same direction as the velocity vector, because the mass has no direction. So the cause of this is the weight force. This object A is in projectile motion, so the weight force acts downwards, and this force downwards causes a change in momentum. Delta P equals force times T. So this force is acting throughout the fall, which means the momentum is changing the whole time through here. And I think that's basically all they need for D. And then calculate the velocity of A at the instant it hits the ground. Now it's a bit tricky, and I think up here, okay, pulse on piece A. So this is just piece A. Alright. So I think we're just going to assume that piece A here, because it has so much of the mass, piece A is basically going horizontal at the start. Bold assumption. So the change in momentum of piece A is the final momentum minus the initial momentum. So we've been given the impulse here, the change in momentum is 3.1. We're trying to calculate the final momentum so that we can work out the final velocity of A. And we're going to subtract from that the initial momentum, which is mv at the explosion. So it's this up here. Yeah, and I'm making the pretty big assumption that theta A is very small, so that all of this momentum is horizontal. So, come on brain, 3.1 times PF minus the mass, 0.8 times 80. Cool, and then do some rearranging here. I'm just going to swap these two around, and then this goes to the other side as well, which means it's plus 0.8 times 80, which is whoa, 64. So P final equals 67.1 kg meters per second. Cool. And then we need to calculate the velocity, so we do that by going P equals V and solving for the velocity by dividing the momentum by the mass. And this is the mass of A, which is 80 kgs, which gives us 0.8399 meters per second. 2, 3 significant figures. Cool, so yeah, pretty big assumption here that this angle is basically 0, but then calculating the velocity by first using the change in momentum equation. Remember, change in is always equal to the final minus the initial. They've given us the change in momentum, the impulse. I've calculated the initial momentum from here to find the final momentum just as the ball hits the ground at Q, or section A hits the ground at Q, and then use that to calculate the velocity. Yeah. Cool, that's all the questions. Hope that helped. Thanks.